And today I'll be talking to you about some work that I have been doing during the course of my PhD on magnesium-ion pyroborate as a novel cathode candidate for high-voltage rechargeable magnesium-ion batteries. And this work was done with, Dr. Sunita Day, who's now at the University of Aberdeen to start her own research group. So I'm going to start by talking to you about my work in the context of magnesium-ion battery research, and then I'll introduce the structure and electrochemistry of my materials. I'll then go into a bit of more in depth about Mossbauer spectroscopy, because it's a technique that was really useful for me to find out the results that I'll be presenting in the talk. And I appreciate that some people here might not be familiar with it, and it is a really interesting technique, so hopefully that will be interesting. And then we'll go on to speak about the results from the work that I've been doing in my PhD. So we've seen a lot of introduction in magnesium batteries, but luckily we haven't seen a timeline yet. So here we go. Single-use or primary magnesium batteries have been around for almost 80 years, and they were widely commercially available and used to date, especially in maritime systems. But the first sort of record of a single-use magnesium-ion battery dates to about 1943, where they were primarily produced to be used for military purposes in World War II. So since then, in the 1990s, Gregory et al. Proposed a rechargeable magnesium battery in a non-aqueous system. And 10 years later, Doron Auerbach's group has published the seminal paper that most people here will know, where he demonstrated the first rechargeable magnesium battery prototype that was stable up to 2,000 cycles. And I'm going to focus in on the cathode of this paper, which was the Chevreul phase molybdenum sulfide. And to date, almost sort of 24 years after this discovery, it's still sort of the benchmark cathode material used in the field. And now the research has been sort of shifting towards looking at high voltage rechargeable magnesium-ion batteries for sort of commercial purposes and attractiveness. And many of the people here may know that sort of the field struggles from some challenges that are intrinsic to magnesium electrochemistry. We've touched on them quite a bit. Slow rates and slow kinetics in intercalation from the magnesium 2+ ion. A lack of stable high voltage electrolytes here, probably I would say compatible with the high voltage cathodes that we have so far. And sort of we haven't pinpointed a high voltage cathode for rechargeable magnesium batteries yet. So my work focuses on sort of developing a cathode material to improve from the operating voltage of the Chevreul phase. And what we did was we took inspiration from lithium-ion phosphate, which has had a lot of commercial success in recent years, and the lithium-ion borate species, which isn't yet used commercially, but has shown really good sort of capacity improvements in the last couple of decades. And so what we decided to work on was magnesium transition metal pyroborates. We chose the polyanion system because it sort of uses the polyanion inductive effect to raise the theoretical operating voltage of the battery compared to sort of the standard molybdenum sulfide. The polyanion group itself also stabilizes the oxygen, and the boron was chosen as it would offer sort of a lighter system and therefore higher gravimetric capacities. So I'm going to present some sort of seminal papers that were done on these classes of materials. If I'm not mistaken, this paper was written by Shuhang Bo at the beginning of his career. And so this studies a magnesium-ion pyroborate with a stoichiometry of 2/3 magnesium, iron 4/3. This was a first principle study where, by looking at bond valence sum maps of the material, they were able to identify these channels for magnesium diffusion that you see here, the IB. And they discovered that there was this sort of parking lot diffusion mechanism where the magnesium could hop out into these channels and sort of move through them, not caring about the sort of site disorder that you have in these like crystal sites. They also did some TGA, and they saw that magnesium was being removed from the structure at high temperatures. And then we've got this other work done on the magnesium-manganese pyroborate system. And in this case, they studied the cathode material for use as a conversion cathode in lithium-ion batteries. They reported a removal of of sort of all the magnesium and insertion of 1.4 moles per formula unit of lithium ions and a reversible capacity of 100 milliampere hour per gram. They didn't show a lot of post-cycling analysis to sort of prove this, and that will sort of end up being important takeaway message from my talk, hopefully. So these are my materials. We synthesized the one-to-one stoichiometry of magnesium-ion pyroborate, which hadn't been synthesized before. And here you can see the synchrotron powder X-ray diffraction collected of the material, where we were able to refine the crystal structure. And we identified a small ion impurity that was coming as an unintended synthesis byproduct from our synthesis route. And it ranged between 4 and sort of 7 weight% based on the synthesis. And these polyanion materials are characterized by these sort of 2 metal sites, M1 in blue and M2, which form these ribbons that extend in the A-axis 2-dimensionally. And they have 2 slightly different chemical environments and are occupied by a disordered occupation of magnesium and iron. So we did some Mossbauer. Don't worry if this isn't yet entirely clear to you. In a couple of slides, I'll go more in depth into Mossbauer spectroscopy and what that means. But I just wanted to show here close to the SIF, the crystal image, that we have 2 distinct iron 2+ sites, which correspond to the 2 metal sites that have slightly different sort of chemical environments due to the disorder of the M2. So we're able to really look in depth at where the iron sits in the crystal structure. And we were again able to see in the Mossbauer with this sort of 4-peak yellow signal, the iron metal impurity. So now focusing more on the key part of my work, we made the material, and what we decided that we wanted to do was to look at whether we were able to remove the magnesium from the cathode structure. So what we decided to do was to cycle the cathode and look at just the first charge in a well-understood electrolyte anode system that could go through the voltage range that we were hoping to charge it at. And so we decided to use lithium metal and LP30 electrolyte, which are some standard lithium electrolyte anode systems that are used. What we see is that we reached almost 100% of our theoretical capacity. And we have this really nice promising electrochemical curve that we would expect to get from a transition of all the iron 2 to 3+ in our material and a removal of about half of the magnesium from the cathode structure. Just to note that the batteries are cycled at C/50 and in an oven, just to sort of help with the slow dynamics of the magnesium. And so if one looked at this just the electrochemistry, it would look really promising. We've got a nice plateau here around 3 volts, and it looks like we're getting almost all our theoretical capacity. But what we wanted to do was to go really in depth and see whether we were removing magnesium from the cathode. And the magnesium removal would be accompanied by an ion redox process. And so we decided to use Mossbauer spectroscopy to investigate whether we were seeing this ion redox process. And so now this is a side on Mossbauer spectroscopy. So Rudolf Mossbauer discovered the Mossbauer effect during the course of his PhD and was one of the youngest people to win a Nobel Prize at age 32 for having discovered the effect. And this is known as the recoilless nuclear resonance absorption of gamma rays. It occurs at energy wavelengths that can be used to probe the hyperfine interaction of atoms. And the hyperfine interaction is an effect that splits the degeneracy of the energy levels inside an atom through the interaction of the nuclear magnetic dipole moment with the electromagnetic field generated by the electrons around the nucleus and the uneven electric gradient throughout the atom. So to understand how a Mossbauer spectra looks like, I'll quickly talk you through how a Mossbauer spectrometer works. So since we're looking at gamma rays, we start with a radioactively decaying isotope of cobalt-57. And this will emit an energy that we're interested in, a radiation energy, and we'll call it Fe star star for simplicity. And these gamma rays of Fe star star radiation are passed through and shine onto our sample or absorber, where the sample that we're trying to study will be placed. And the ions, the ion 57 isotopes sitting inside our sample will absorb the gamma rays when the energy of the gamma ray matches the energy of the ion inside our sample. The gamma rays that are not absorbed are transmitted through and collected by a detector, and we collect a sort of transmission spectrum here. The key importance is that the energy that the ion 57 isotopes absorb when they're sitting inside the sample is slightly shifted from the Fe star star radiation. And this slight shift in energy depends on the chemical and physical environment that they see. So what we decide to do, what Mossbauer discovered was that by moving the source left and right, you could use the Doppler shift and change the energy of the change the energy of the gamma rays that the ion 57 isotopes see inside the sample. And therefore, you can sort of probe all the energy shifts that you're interested in when looking at the different chemical and physical environments. So a Mossbauer spectra will typically look like the one you see here. We've got the intensity of transmission on the y-axis, and we've got the velocity of the source as the x-axis in meters per second, which can be related to the energy of the gamma rays. The Mossbauer spectra will have two typical features which we're interested in looking at today. The quadrupole splitting, which is the distance between the two doublet peaks, and the isomer shift, which is the distance of the center of the two peaks from the zero velocity. And by looking at the combination of these two values, we're able to really clearly pinpoint the ion oxidation and spin state when it's inside our sample. So this is a map that shows all the different sort of combinations and how we associate them to different ion oxidation states. So now we're going to revisit quickly the spectra that I was showing you at the beginning of the talk for my pristine material. And the the quadrupole splitting and the isomer shift tell us that we're in the ion 2+ oxidation state. And for reference, if we were seeing some ion redox in our cathode through charge, what we'd expect would be a shift of the center of the two peaks towards a lower value of about 0.4. So we'd really see the two peaks shift to lower values. Right, so just in general, battery applications of Mossbauer spectroscopy, it's really useful for studying pristine electrodes. It's quite a good local probe of the environment that atoms sit in the crystal structure, and it can give you a lot of information about the electric and magnetic interactions of the ions. It's also really good for studying polycrystalline, amorphous, or nanoparticles, where you would typically struggle to use X-ray diffraction to characterize the materials. And it can be adapted to a lot of operating conditions because it's such a simple setup. And so you can investigate a lot of reaction mechanisms under Operando conditions. These are just some examples of how it's been applied to battery materials before. I'll highlight alloying materials here, as sort of might be particularly interesting. And then here, just to show an example of lithium iron phosphate, where they were able, by looking at the Mossbauer superimposed with the charge cycling, they were able to sort of quantify the exact fraction of iron 2 to 3+, and sort of map it to the charging position of the battery. So during my PhD, I received some funding to go and work at Montpellier on Operando cells. I thought this might be interesting as well. So this is the Mossbauer spectrometer. It's sort of large enough to sit on top of a desk. The cells are very similar to Swagelok cells, stainless steel. They close using a spring mechanism and a screw. The difference being that you have beryllium windows to let the gamma rays through, and you wouldn't want to use sort of heavy metal current collectors because they would also block the gamma rays. So you would tend to use PTFE self-sanding films. And then the battery kind of sits on top of the source and underneath the detector. And you can cycle it there while the spectra are collecting. So another thing is that to collect a good signal-to-noise ratio with your spectra, you need to be sort of collecting from 2 to 4 hours. So Operando measurements work really well for magnesium, where you're cycling really slowly anyway. If you were wanting to look at slightly faster charging materials, then you could do sort of interval pulses of charging and then relaxation while studying your material. So now back to my work and how the Mossbauer was useful in determining what was going on inside our cathode material. Just as a reminder, this was the promising electrochemistry that we were looking at. And what we, again, were looking to find out was whether we were removing magnesium from the host cathode structure. So at the very early stages of the research, what we did was we started with some Ex-situ analysis. So we took some coin cells, cycled them, took out the cathode powders, and sent it to a synchrotron. And we collected 3 main sort of stages of the charge at the end of the 3-volt plateau that we see, and then at the end of the 4.2-volt charge with the CCCV. And what we're able to see here is that there isn't a large change or a significant change in the main cathode structure. So this isn't, we didn't consider this as conclusive proof of the fact that we weren't demagnesiating the structure, because polyanions have the polyanion system. One of their strengths upon demagnesiation or delithiation is that they don't change in volume that much. So in principle, a lack of change of structure for these materials doesn't actually mean that you are not magnesiating that much. And what we did see, however, was that the peaks here, which are sort of zoomed in on the insets, that we associated to our iron metal impurity, if you remember, it was this 4 weight percent that was coming out of our synthesis, were disappearing throughout the first charge. We also ran some SEM EDS, and it didn't show significant demagnesiation from the surface. I'm not going to show the results here, but what I wanted to show in the pristine material is that you can clearly see the morphology of these iron metal impurities sort of segregated from the main phase of our cathode material. So this is the Mossbauer that we collected. We went to do some Ex-situ to figure out really if there was any ion redox going on in our material. There's a lot going on here, so I'm going to guide you through it. So the first thing is the center of the 2 doublets is not changing. It's not shifting down to lower values. So we're actually, unfortunately, not changing our ion redox. Again, as a reminder, if we were seeing any sort of ion 3+, we would at least see some doublets shifted with a center at around 0.4, which we don't see. So the iron 2+ oxidation state persists throughout the whole charge. We also see that the iron metal impurity, again, like we were observing in the synchrotron, disappears after the 3-volt plateau. So it's sort of, it's consumed during this first plateau process. And another point of note is that we see this other iron 2+ environment. It's not 3+, it's 2+ at the 3-volt charge, which then disappears at the 4-volt charge. So what was going on? We were able, through the Mossbauer, to tell that we weren't sort of changing the ion redox, and we were able to see that we were losing this iron metal impurity. And we also did some Operando XANES, where we were looking at the iron K-edge as well. Here, typically with battery materials, if you were studying the XANES, you would expect a shift of this pre-edge position with oxidation, and it's not happening, or reduction, and it's not happening. So we know that there is no ion redox and that likely our cathode phase is not demagnesiating. So we didn't want to stop here. We wanted to try and figure out what was actually going on inside the battery to sort of inform in future what could be important to take care of while making these materials. And we went in to look at sort of what could be the process leading to this electrochemical capacity. So what we see is from powder X-ray diffraction, some Mossbauer, the EDS, and some additional magnetization, is that we've got an irreversible consumption of the iron metal impurity. There are some previous studies of iron metal current collectors in battery electrolytes. And what they show is that around 3 volts versus lithium, you start seeing these really strong corrosion currents. And so what we propose is a direct electrochemical oxidation reaction of the iron metal in our sample through a 2-electron process. And when we sort of did some math to figure out what capacity we'd expect based on the weight percentage of iron that we have in our cathode, we see that we'd get about 40 to 70 milliampere hour per gram, depending on the specific synthesis. And that matches really well with sort of this plateau that you see below 3 volts. So the iron metal is going away, but what's happening to it? We did some solution electrolyte NMR. So what we did was we compared the NMR of the electrolyte when it's just sitting in the glove box with some electrolyte extracted from a coin cell cycled to the end of the first charge. And from the proton NMR, what we can see is that this 10.5 doublet signal, which is the HF, that's present in sort of the electrolyte because of water and sort of the fact that the electrolyte's been sitting there, is consumed throughout the charge. What we also see when looking at 19-fluorine NMR is the presence here in the charged material of oxyfluorophosphate salts, which are associated to LiPF6 hydrolysis, and LiPF6 is the salt that we're using in our lithium-ion electrolyte. So LiPF6 hydrolysis produces further HF. So what we know is we have HF in the electrolyte that's being consumed, and we have reason to believe that we're making even more HF, but we don't see it at the end of charge, so it's sort of being consumed in the first part of the charge. And the hypothesis would be that the sort of this redox reaction of the iron metal is initiated by the proton attack from the HF on the native oxide film coating. So Jelena mentioned that there's sort of metals have native oxide coatings. Our iron particles sitting in the electrolyte probably do as well. And we started looking at some other studies that reported iron metal studies of current collectors in electrolytes. And what we found was a study by Gutian et al., who saw that they were sort of forming porous iron fluoride coatings throughout the first charge. When they were studying the iron metal corrosion. So what we did was we went back to look at our EDS maps, and we found regions on the conductive carbon surface, which are very distinct to sort of our cathode phase, that were coated with a lot of fluorine. And we also looked at the Mossbauer. If you remember, there was this additional 2+ peak at the 3-volt charge. And this green Mossbauer signal ended up being consistent with iron fluoride. And so what we think is happening to our iron metal is that it is sort of reacting out through proton attack. It's then depositing into iron fluoride below the 3-volt, as we know from the literature. But then we don't see it at the charge again. So there's a lack of this iron fluoride signal at the 4-point charge, and this is actually further sort of consistent with other reports of corrosion currents that show that the corrosion coatings, when you raise the voltage even higher, start dissolving off iron species from the surface. So in conclusion, what we think is the mechanism that's going on is sort of highlighted in this figure here, and it's consistent with sort of the whole suite of post-cycling analysis techniques that we applied to this material. What really is the source of this capacity at higher than sort of 3.2 volts when we lose the plateau of sort of the iron metal consumption? It could be a series of things. It could be the iron species dissolving into the electrolyte, undergoing further reactions. It could be electrolyte degradation, because the cell at this point has been sitting 50 or so hours at 55 degrees. And it could also be reactions with an amorphous coating layer of the polyanion system. And this is something that I've been investigating in my current projects, is that we think there's sort of an amorphous borate coating on our materials, and that this could be undergoing further reactions, which are they just sort of go away at the end of the first charge, and they're not reproducible. And so we are investigating this mechanism in polyanions without iron metal impurity. So as a conclusion from sort of the PhD project that I've been doing so far, when looking at our magnesium-ion pyroborate in the structure or in the system that we're looking at with the lithium, we conclude that it's ionically insulating and doesn't appear to change bulk structure. We did a few sort of attempts in magnesium electrolytes, but they didn't really go very well at all. And what we notice as well is that there's no proof of demagnesiation even when the iron metal is not present. So really recently I've been able to finally synthesize this material, which is quite finicky to make, without this iron metal impurity. And you really don't see the demagnesiation. So it isn't the fact that we've got this going on that's sort of stopping our material from demagnesiating. And then what we've seen is tracking sort of with this iron metal impurity, we've identified a possible reaction mechanism. Hopefully I've shown you that Mossbauer can be useful, would be useful to track the ion redox if my material were demagnesiating, but also it's really useful in probing possible side reactions that could be going on inside your battery. So we had this sort of small 4% and we were able to see it disappear. And I'm going to leave with a thought from a paper by Jordi Cabana, which I really like. And it's sort of, he discusses the fact that there's some discongruence or confusion when looking at metal oxide cathode materials for magnesium-ion batteries, and there seem to be confusing reports on their performance. And that this often stems from an over-reliance on measured capacity and at most structural changes of the magnesium. And what he says is that, competing reactions, including with the electrolyte, can generate really similar behavior to sort of the good capacity and at best structural change. And I mean, this work might not be, an incredibly great result, but it is like a very good example of this sort of mechanism where if you sort of looked at the electrochemistry, you'd say, that looks really promising, but in reality, when you go in depth, it's a small impurity and a lot of side reactions going on. And with this, I'd like to thank you for your attention. I'd like to thank my supervisors, Dr. Sunita Day as well, who's now in Aberdeen and taught me everything I need to know about magnesium batteries at the start of my PhD, and Dr. Moulay Sougrati from the Institut Charger à Montpellier, who hosted me and collected a lot of the Ex-situ data. So thank you once again for listening, and if you have any questions, I will do my best to answer them.